Hello everyone. This is the fourth and last lecture of the physical chemistry chapter specific heat of solids, where the Deby's T-cubed law will be discussed. Debye avoided the most serious assumptions of the Einstein's theory and suggested that number one, the crystal behaves like a huge molecule. Remember, in the Einstein's theory, the solid substance was assumed to be aggregation of atomic oscillators, but here it is taken to be a huge molecule, wherein the motion of any atom affects the motion of the neighboring atom. Remember, in the Einstein's theory, the atomic interactions was absent, whereas in this theory, it is present, the atomic interaction. So the neighboring atoms will be affected. Number two, the three NM modes of vibration in one mole of a monatomic solid are not at all identical. Look, in the Einstein's theory, there was a common mean frequency nu, but here this vibration is distributed among a spectrum of frequencies, and the frequencies range from 0 to a maximum frequency nu m. And this nu m is considered here. This nu m is taken as calculation. And this nu m is related with Einstein's nu by this relationship. It is equal to 4/3 nu. Nu m is equal to 4/3 of nu. So it is a little bit larger than this nu because this is the maximum frequency. Okay, and this one was the common mean frequency. And this nu m is the characteristic of the solid. And this model treats atomic vibration within the crystal lattice as quantized sound waves. That means like the phonons. So the atomic movements can be compared with the movement of the quantized sound wave movement. That is the phonons. Now, the undergraduate student need not derive this equation. You can directly go to the final form of this Deby's T-cubed law. This Deby's T-cubed law has the form: the heat capacity at constant volume is equal to 12 by 5 pi to the power 4 Na into K into T by theta D whole cube. Here, theta D is the Debye characteristic Debye temperature. Okay, and it has the expression h nu m by k. So in the Einstein's theory, it was theta epsilon, which was h nu by k. But here in the Debye's theory, it is theta d, which is h nu m by d. That means theta d is equal to 4/3 theta epsilon. So here this Na is Avogadro's number and this is Boltzmann constant, and their product must be equal to R. And we know the value of pi, we know the value of R in calorie per Kelvin per mole unit. And if we put this value, we get this 12 by 5 pi to the power 4 R as 464.6. So look, theta D has the expression h nu m by k, and this is the characteristic Debye temperature of a substance. Now, this 464.6 and theta D cube is yet another constant. So let us write this equation in this form. Just take this theta D cube here, just denominator of 464.6, and separate this T cube part. Then finally it gets the final form Cv equals to A into T cube. That means A, this is an empirical formula. And this is the most important formula which will be utilized in determining the absolute entropy of a substance from the third law of thermodynamics. So in the third law of thermodynamics chapter, this relationship is very much useful. Now this A should have the dimension of Cv by T cube. That means it should have the unit of calorie per Kelvin per mole per calorie cube. That means calorie per Kelvin to the power 4 per mole. And this is the well-known Deby's T-cubed law, where A has the value 12 by 5 theta D cubed pi to the power 4 into R. And this is known as the Debye constant. This empirical constant is known as the Debye constant, which is the dimension, this one. So the Debye equation predicts that the heat capacity of a solid is a function of temperature and depends upon only the characteristic maximum frequency nu m. Now this is the graphical presentation, back to back Einstein and Debye. This is T by theta. In case of Debye, this is theta D. In case of Einstein, this is theta epsilon. And here CV in calorie per Kelvin per mole unit. So these two, if compared, they will appear like this. Debye will be placed above Einstein. Now the success and failure and its corresponding explanation. The success of the device T cubed law is this law is in good agreement with the experimental data at lower temperature. In case of Einstein's theory, it was successful in the higher temperature range, but it didn't come to agreement with the experimental values in the lower temperature range. And for even more complicated crystal structures, in case of Einstein, only for it was in not only Einstein and Dulong Petit, they were only successful in case of metals and at high temperatures. But here, uh, for non-metals also, or more complicated crystal structures for solids, solid with more complicated crystal structure, it's successful, and lower temperature, it is very much useful. At higher temperature, it is actually not so much useful. So its failure is agreement with experimental data at higher temperature is poor. Why this one? Look, it has been explained like this. The replacement of the actual distribution of vibrational frequencies by an oversimplified distribution function where the crystal structure is ignored. And this is the reason for this disagreement. That means in the crystal structure, maybe it is complicated, but its complicated forms are ignored. That means the bonding in between the atoms within the molecule was were not so much considered, and that is why only it was taken as a molecule. It's a huge molecule, but apart from that, there had been some complications which were not taken into consideration. That is why this disagreement is observed, particularly at high temperatures. So that's all about the device T cube law. You must keep this law in your mind before starting the third law of thermodynamics. The law is CV equals to A into T cube. That's all. This is the most important thing. Okay, so that's all. Thank you and have a nice day.